Hello everyone. So today we'll be discussing about the XOR problem, or you can say the implementation of XOR problems in neural networks or in networking. So consider the task of computing elementary logical functions of two inputs. So inputs like x1 and x2. These are the two inputs. Okay, and we are performing different logical functions like and or XOR. Okay, so these are the different functions that logical functions that will be applying. So the truth table, if you can recall, is where x1 and x2. Okay, so x1 x2 for y is 0 and 0 is 0, 0 1 is 0, 1 and 0 is 0, 1 and 1 is 1. And for OR function, okay, the same x1 x2 input, okay, if we apply OR function, it will be 0 0 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. And for XOR, the truth table is x1 x2, okay, will be 0 0 0 is 0, 0 1 0, 1, sorry, 0 1 is 1, 1 0 is 1, and 1 1 is 0. Okay, so this is the XOR function for, okay, if you're this is a truth table for the XOR function. Now this example we was shown for the perceptrons, which is a very simple neural unit that has binary output and does not have a non-linear activation function. So the output y here, so output y perceptron, okay, is nothing but equal to either two inputs, that is either 0 or 1, okay, and is computed as like if w dot x plus b is less than or equal to 0, or if w dot x plus b is greater than 0. Okay, so if w dot x is less than 0, then the perceptron output will be 0. If w dot x, that is if you are computing w dot x plus b, if the value is greater than 0, then your perceptron output will be equal to 1. So it is very easy to build. Now this is the how we are actually applying the non-linear function, okay, or that's the activation function that is being applied to the perceptron. Okay, now it is very easy to build and or the and the OR function with perceptrons, because you can see that if I am saying taking this equation into consideration, and you have seen about the and truth table where x1 x2 and y for that matter, okay, where 0 0 is 0, 0 1 is 0, 1 0 is 0, and 1 1 is 1. So if you are taking here x1, okay, so and x2, these are the two inputs, okay, and plus 1 is nothing but the one more input, which is nothing but the bias input. Okay, so this one you can say that here you can take x1 as somewhat this is nothing but the weights that are applied, that is w1 and w2 are nothing but the weights, okay, and bias is nothing but b. which is nothing but minus 1. So here this 1 which you can see here is nothing but the weights. This is nothing but W1, this is nothing but W2, and this is nothing but the biases, okay, that are applied. So by W1 is applied to X1, W2 is applied to X2, okay, and okay, when we give this to the node, okay, so we here perform the what do you say, the AND function. So what does AND function do? So here AND function, what it does is, so your x1, if it is equal to for in this case is equal to 1, okay, so I'm taking this as into consideration, and x2 is equal to 0, and you can see here your weight 1, w1 is equal to 1, and w2 is also equal to 1, okay. So what happens here is, if you're applying the equation w1 x1 plus w2 x2 plus b, okay, okay, which is nothing but equal to z, okay, which is nothing but equal to z. So this is how the z what you get. Now w1 is what is 1, x1 is nothing but 1, plus w2 is what 1, x2 is nothing but 0, plus b. What is b here? B is nothing but your minus 1. So minus 1 means, so I'll directly write as minus 1, okay, I'll write as minus 1. So this is nothing but z, so which is nothing but 1 plus 0 minus 1, which is nothing but 0. So your z will be nothing but 0. So which is nothing but correct as per the truth table. You can see the truth table says that 1 and 0. If your x1 is 1 and x2 is 0, then your output will be 0, which is what you can see over here. Now same thing if you take the another instance where instead of x1 x2 is equal to 1, if I am taking x2 as equal to 1, okay, so x2 is equal to 0, I am taking x2 is equal to 1. So here instead of this 0, let me write it as 1 here. When you write it as 1, so this will become 1 plus, okay, sorry, so 1 plus 1 minus 1, it is nothing but, okay, nothing but this will be nothing but 1. So that is what it is true. So I am taking this truth table. So if my both x1 and x2 are 1, then your output is 1, which is nothing but true. Okay. Now this is about your AND function. The same thing if you are applying for the OR function for that matter. Okay, so OR is nothing but your truth table for OR is nothing but x, okay, and y, sorry, x1 and x2 and y, where x1 is nothing but 0, 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 1. Now the same criteria for OR. So if it is your W1 x1 plus W2 x2 plus b. So now what will happen here is your x1 anyway, let me take 0 and x1 is equal to 0 and x2 is equal to 1. Now what will be the output? Your weight is nothing but W1, W both are 1 only. So 1 into 0 plus 1 into 1 plus, okay, your bias in this case, if we take is 0 for that matter, okay, so 1 into 0 and 1 into 1, so this will be 0 plus 1, okay, and bias if we take it as 0, okay, so it will be nothing but equal to 1. This will be nothing but equal to 1, okay. So if you are taking b as uh, b is equal to 0 here, okay, and you are applying in this. So what you'll get is, okay, the output is 1. So that is what you can see here. So this, that is what you can see, that the output is true. So 0 and 1 is 1. Same way, if you're applying uh, x as 1 and this is nothing but you can say that 1 into 1 plus 1 into 0 plus 0, which is nothing but again equal to 1 only. Same way, 1 into 1 plus 1 into 1 plus 0, which is nothing but again this will be nothing but 1. But if it is something like 0, if I'm now, you can say these three conditions. So this is about the this condition, and this is nothing but this condition. If it is like x1 is 0, so 1 into 0 plus 1 into 0 plus b is 0, so it will be nothing but equal to 0. That is why you can say that this condition, okay, is 0, which is nothing but true. Okay, so here this is nothing but my w1, this is nothing but x1, this is nothing but w2, x2, and this is nothing but b. Same way, this is my w1, x1, w2, x2, and b. This is also my w1, x1, w2, x2, and my b. Okay, so all we can say we can, it is proved that, okay, okay, if you are taking your b value as 0 and you are performing this truth table, okay, you are performing the XOR function, sorry, OR function, okay, this is the output which you will be getting. Now when you are taking the next aspect, that is you want to see how the XOR function works. So for XOR, things are not as straightforward as it looks like. Okay, so for that, you have to. This can be only be seen with respect to the example where here x1 and x2. Okay, let's take this example where you can see that this is my, okay, x1, okay, versus the x2. Okay, so this is my x1, and you can see that this is my center point where I can say that my 0, that is if my x1 is 0 and x2 is 0, the output is nothing but 0, because that is your in as per, and you can say that if my x1 is 0 and x2 is 0, if both are 0, then my output is 0. If my x1 is 1, if my x1 is 1 and x2 is 0, then your output is still 0. If your x2 is 1 and x1 is 0, still your output is 0. That is why you can say still you can see that output is 0. But in the case of if both x1 and x2 are 1 and 1, which is somewhat over here, okay, which is nothing but somewhat over here. Okay, so if both are 1 and 1, then you can say that, okay, it is a 1. So you can see the output. I put this darkened circle, which says that, signifies that your output is, okay, 1. Now, what does it say? See, if your x1 is 1 and x2 is 0, then output is 0. If your x2 is 1 and x1 is 0, okay, your output is 0. If both x1 and x2 both are 0, still it is 0. But if your both output x1 and x2 are 1, then it is 1. So I am actually putting a line, linear line here, which shows that anything below this are 0, anything above this are 1. So that is what you can easily classify, make classification. Okay, that is for 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, 1 and 1 is 1 for AND. Okay, same thing if you are taking for OR function like x1 or x2, if you are taking this function for that matter. So your x1 is there and x2 is there. Okay, so what does OR function say? OR function say that 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 1. So in this case, you can say that your when one of your input is 1 and another input is 0, then it is 1. So when my x1 is 1 and x2 is 0, it is 1 only. If my x2 is 1 and x1 is 0, still it is 1 only. And if my both input x1 and x2 are 1, then also it is 1. But if my both the inputs are 0 for that matter, so this is my 0. Okay. In that case, if it is 0, then it will be 0. So I'll just write it over here. So it will be nothing but 0. So I am not darkened it, it will nothing 0. So you can say that in this case, anything above this, you can say, sorry, anything um, okay, above this particular line, okay, anything above this particular line. That is, if your x1 is 1 and x2 is 0, or x2 is 0, x2 is 1 and x1 is 0, you can say that even if one of the input is okay is 1, then you can say that it is having the okay positive output. So that is what or you can say 1 as the output. That is why you can say that in or I can say uh, the 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 linear line is over here. Okay, that is below these two line, these 2 points. Okay, where because it says that after this everything is plus, it is nothing but your 1 only, and below this is nothing but your 0. So that is your and or. But when it comes to XOR, your XOR table is slightly complicated, where you can say x1 and x2, and if you are applying XOR there, okay, so 0 is 0, where 0 1 is 0 1, sorry, 0 1 is 1, 1 0 is 1, and 1 1 is 0. So what happens here is, okay, here you can say that you for this for this case, okay, okay, we cannot do it uh, directly. So even if you want to, okay, you see that the graph for this, you can say it will be slightly complicated. You can say that this is my graph for my XOR, your x1, then this is your y1, and sorry, x1 and x2, and you can see that this is my one of the input. Even if one of the input is 1, okay, that is if either x1 is 1 or x2 is 1, okay, okay, sorry, you can that time you can say it is the output is 1 only. But if both the inputs are 0, then it is 0, okay, and if both the inputs are 1, still it is 0. No, so it becomes slightly confusing, okay, where I should put the line, because it says that below this also it is 0 and above this is also 0. So only this particular part you can say it is 1. So for that matter, okay, if it is not possible to compute the XOR with perceptrons, okay, so crucially these perceptron equations given like x1 and x2, okay, equation of the line is b is nothing but w1 x1 plus w2 x2 plus b is nothing but equal to 0. The standard linear format, the standard linear format is nothing but your x2 is nothing but equal to minus w1 by w2, okay, into x1 plus minus b by w2, okay. So this is nothing but my slope. You can say this is my slope. So this line, okay, acts as a acts as a decision boundary decision boundary, okay, in two-dimensional space. In two-dimensional space. So the output 0 is assigned to all inputs lying on the one side of the line, and output 1 is assigned to all inputs to the other side of the line. So if there are more than two inputs, the decision boundary becomes the hyperplane of the line. So idea is same, where you can separate the space into two categories. Okay. Now, solution to this XOR is uh, by bringing different layer to the network. So you can see this. This is the solution to the XOR problem. So XOR can't be calculated by a single perceptron. So it can be calculated by a layered network of units. So I once again write the XOR, where X1 and X2 and my Y is nothing but the truth table output of the XOR. So 0, 0 is nothing but 0, 0, 1 is nothing but 1, 1 and or 0 is 1, 1 or 1 is 0. Okay. So here, if my X1 and X2, these are the two inputs. Okay. And so as I said that it cannot be done with single perceptor. So this is nothing but my hidden layer H1 and H2. Okay, H1 and H2. So the weights what that is applied here, W1 and W2 are nothing but 1 and 1. So W1 is 1 and W2 is 1, as we had seen in that time in the example. Same example I'm using. Okay, so W1 is 1 and W2 is also 1. Okay, so that is applied to both the hidden layers. Okay, now for the there is one more bias layer, that is +1, which is the bias layer, where you can see that for this particular H1, okay, we are giving, sorry, for this particular hidden layer, okay, so the input is 0, that is the bias is nothing but 0. Okay, and for this particular hidden layer, the bias is nothing but here minus, okay, 0 and -1. Now you can see that this is nothing but your y1. Y1 is nothing but output. Now to this, okay, my weights will keep on changing. So I can give weight as 1, and this the weight as -2, and here I am giving the weights. Okay, here this is nothing but my bias. Okay, which is nothing but 0. Okay, 0 is given. Okay, as the bias. Okay. So initially, let me take the first iteration, considering the input as, okay, x is equal to 0, 0. If you multiply each input, okay, so multiply each input value by the appropriate value. So you'll get here h1 is equal to, okay, you can say this is my h1. H1 is equal to, okay, ReLU of, okay, 0 into 1 plus 0 into 1 plus 0. Now, why it is like that? See, is that my weight is nothing but here, is nothing but 1. W2 is also 1. But what is the input I have taken here? 0 and 0. X1, X2 both are 0. And one of the bias, first time I am taking the bias for H1 is nothing but 0. That is why here 0. So what will be my H1? H1 is nothing but, okay, I am using ReLU function, activation process, ReLU of 0, which is nothing but equal to 0. Same way, I'm doing it for h2. So h2 is equal to ReLU function I'm applying in the first layer. Okay. So it is nothing but uh, again it is 0 into 1 plus 0 into 1 minus 1, because why minus 1? Because now the bias is nothing but minus 1. So which is nothing but h2 is equal to ReLU, okay, of minus 1, which is nothing but minus 1 is nothing but when I'm applying ReLU function, okay, it is nothing but anything if it is negative, that will be tend towards the 0 only. So that is what ReLU function is all about. Okay. If you have any confusion about ReLU function, you can visit the video about the explanation of ReLU function. Okay. Now we can see that h of, okay, 0 comma 0, okay, is what we had seen right now. Okay. So this h of 0 comma 0, okay, when it is applied, okay, applied to the y, so what we'll be getting here is y is equal to, okay, 0 into 1, okay, plus 0 into minus 2 plus 0. Okay. Now why it is like this? You can see this one. So my h1 is what now? H1 is nothing but 0. H2 is 0. So 0 into 1 plus 0 into minus 2. Okay. Plus 0. So this is my bias. So that is 0 into 1 plus 0 into minus 2 plus 0. So y is nothing but equal to 0 plus, okay, 0 plus 0. Okay. So again, your y what you'll be getting is nothing but your 0. So that is what it is true. So when your x1 and x2 are both are 0, then you'll get y as 0. Now you can try the same thing for other thing like x1 x2. You can also the same by using the same ReLU function and all, same setup. Okay, you can do it for 0 1 1 0 1 1. So it is for you. Okay, you have to try from your side and you can just check. Okay, that with 0 and 1 you'll get 1, with 1 and 0 you'll get 1, and 1 and 1 you'll get it 0. So you just try it yourself. Okay. So now the the hidden representations. Okay, the hidden representation which we had seen for the XOR. So I discussed in the previous slide where if your x1, any one of the input is 1, okay, the output is 1. So that is why it is darkened. If both your inputs are 0, then it is 0. If both your inputs are 1, then it is 0. So this is the original X space. The original X space. Okay. And so it is so it is also instructed to see the intermediate results of output of H1 and H2. So in the original X space, you can see that, okay, 0 X XOR 0 XOR 1 and 1 XOR 0 will return 1. Okay, now let's see the after applying the H layers. Okay, what kind of output you will be getting. So this is after applying the H layers. So this is my H1, this is my H2. Okay, so here you can see that my in beginning. So what happens here is when both your, so what we're combining here is when your uh, x1, this one, or you can say this is my x2, sorry. So if one of the input is 0 and another input is 1, okay, so that was the case over here. So now this particular aspect we are actually combining over here, and I am writing this as h1 comma 0. Okay, so I have combined these two aspects, and I'm just mentioning that. So anything, Okay, below this linear line is nothing but your 1, and anything you can say uh, above that line is termed as 0. So even if it is your 1 1 also, okay, so 1 of 1 is nothing but um, your 0 only. So 1 of 1 also is 0 0 0 0 only. And even if one input is 0 and one input is 0 and another input is 1, so by combining the two aspects, okay, I have made into this as h1, so h1 and h2. So you can get it as the this is nothing but the new linearly separable, the new linearly separable h space. Okay, so you can notice that x is equal to 0 comma 1 and x is to 1 0 1 comma 0 have been merged into single point. Okay, that hidden value will be 1 comma 0. So this merger makes it easy to linearly separate the positive and negative case of XOR line. In other words, we can view the hidden layer of network as forming a useful representation of the input. So in this example, we stipulated the weights, but for the real example, so the weights for the neural network are learned automatically using backpropagation algorithm. Okay, so that is the that is all about the solution to the XOR problems. Okay, so thank you for patience of listening to this. So thank you everyone. Okay, if you have any queries, you can ask. Thank you.